So general function analysis starts with asking about the domain and range. Those are, of course, the big ones we always need to think about when working with functions. And the intercepts, because the zeros of the function are also quite important. The y-intercept, maybe not so much, but the intercepts in general. There are also other properties, though, we can look at a graph and describe. So we like to look at all these things whenever we're looking at any kind of graph because it might help us define the behavior that we're looking for or answer some kind of question. For this first one, we've actually already seen this. As we go left to right, or as x goes to positive infinity, that's left to right, where does the function go? Now, it's important to note that this is different than looking at the end behavior of a function. In this case, we have a function here. This is going to be some kind of polynomial. It's a cubic polynomial, most likely. It goes down as we go to the left and up as we go to the right. That's the end behavior. But here we're talking about not the end behavior, but how does a function behave as we go only left to right. We've seen this in linear functions. If it goes upward, it's an increasing portion of the domain. If downward, it's decreasing. And of course, if it's just flat lines across any portion of the domain, it is constant. Now, linear functions only exhibited one of these three behaviors. It was either an increasing linear, a decreasing linear, or a constant. And we saw in quadratic functions, they could be decreasing then increasing. That meant the vertex was a global minimum. If it was increasing then decreasing, so decreasing then increasing looks like this. Increasing and then decreasing looks like that, and that would be a global maximum versus a global minimum. So quadratics had two portions of its domain, but any general function you're looking at can have any number of portions of the domain that have one of these three behaviors. Of course, as a linear function, we also looked at vertical lines. These are not linear functions because they're not functions at all, and those were neither increasing, decreasing, nor constant. It's going to always be one of these three descriptions. So for this function, we have an increasing portion of the domain. As we go left to right, again, left to right, the function's going upward and upward and upward until it reaches a maximum right here. That maximum happens at -1. So we're going to say it's increasing on this portion of the domain from -infinity to -1. And you're going to use open intervals to define these. So never a square bracket is going to be used. Now it's actually decreasing at this point. It starts decreasing to this point here. So everything between -1 and +1 here is where this minimum is at. This portion is decreasing. And then once again, you can see at this global minimum, or sorry, local minimum, it's not global because this function portion goes down further. At this local minimum, it's going to start increasing again. So this portion of the domain, it's increasing again. So increasing from 1 to infinity. And that was everything. So there are no constant intervals for this one particular function. Okay, now extremas, we've looked at these before. They're the function's turning points, are also called the peaks and valleys. Low points are minima as a plural version of that. High points are maxima. So these are what are called the extrema. The minima and the maxima are the local mins and maxes, things like that. Now the global, as I've said before, global minimum, minima, and maxima are the lowest and highest values a function reaches over its full domain. These may not be the same as the local version. So it depends on where you're looking at. Every global minima and maximum are also local ones, because if you're looking at only a smaller portion, that may look like it's just a local one. But if you view the entire function, then you can see, well, that's actually a global minimum or maximum. So it's important to keep in mind the difference between local and global when you're looking at any kind of function. Okay, where are the local extrema for the graph above, and what are they? So for this graph, we have two extrema. We have this point right here and this point here. This point is a maximum, of course, and this is a minimum. And the question is it local or is it global? Well, it's a local maximum here because the function increases on this side. So it cannot be a global maximum. So we're just going to call it a local maximum. And this one is a local minimum because the function down here increases indefinitely downward. So it cannot be the global minimum of the entire function. So it's a local minimum. Now, these are located at the x value. So the local maximum is located at -1. And the local minimum is located at +1 because they're located at the x value. Now, the actual maximum, however, is the y value of this thing. So the maximum of this function, or I should say a local maximum of this function, is at +1. A local minimum of this function is at -1. So it's located at the x value. The local max was at x equal to -1, right? The maximum was located at the x value, and it is, so is y equal to 1. That's what they are, is the y value. The local minimum is located at x equal to +1, and it is y equal to -1. Now, I should say that global is actually also use the word absolute. It's same kind of idea. Global and absolute are mean the same kind of thing for what we're talking about here. Now, are these local extrema the same as the absolute extrema or the global extrema? No, because this function continues indefinitely downward and indefinitely upward. So these cannot be global or absolute extrema. They're only local. Okay, another type of thing. So we talked about increasing, decreasing constant behavior. We've talked about, maxes and minimum. Now we also talk about symmetry. Symmetry is very useful in a lot of things. We've actually already seen symmetry across the axis of symmetry for quadratic functions, but there are general symmetry that we look at for functions, and they are always based on the Cartesian coordinate system, the actual axes of the graph, so the x-axis and the y-axis, not to the function itself. So every quadratic had an axis of symmetry, but not every quadratic has even or odd symmetry, because it all depends on if it's located, well, where it's located at on the axis, the overall graph that we're looking at. So even symmetry, it looks like the monomial parent function x squared. This does have even symmetry, because if you look at the y-axis here, this thing reflects directly across it. So this is exactly what the same kind of symmetry we looked at for quadratic, but it's only the case if it's symmetric across the y-axis, not specific to the parabola shape. So this is called even symmetry. You can always think of that because this is x squared, and that's an even power on the square. Odd symmetry looks a lot like x cubed. And this is called rotational symmetry, because if we were to flip this thing 180, this point would rotate down there. This point would rotate down there, and this point down there, and we get the exact same graph again. So it just flips by 180, or I should say rotates by 180 across the origin point. A key thing to note is here we're talking about the y-axis. Here we're talking about the origin of the graph, not of the function. And this is called odd symmetry. X cubed has an odd power in it, so it's odd symmetry. Now, that's how you can locate symmetry based on the graph. Now, how do we locate symmetry based on the algebra? Well, that happens if f of negative x, you plug in negative x, if you get out, or if you simplify the function down and you get the same exact thing as f of x, this is called even symmetry. If, however, you plug in negative x and you get out negative of f of x, this is odd symmetry, and that's how you prove it has even or odd symmetry. So for s of x, we have x squared, right? If we plug in negative x into s, we get negative x squared. But that's just the same thing as negative x times negative x. Those negatives cancel, and we get x times x. X times x is x squared. And you can see that's the same thing as the original function. So s of negative x from this portion equals s of x. That's the exact same thing I have written here. So it's got even symmetry. Likewise, for odd symmetry, c of negative x, c was right here. C of x is x cubed. So c of negative x is negative x cubed. We have 3 versions of negative x. 2 cancel, and 1 remains. That can be brought out in front. And we have x times x times x. That's just going to be negative of x cubed. X cubed is c of x, however, so we have negative of c of x. So we've proven that c of negative x equals negative c of x, which is exactly what I have written here. Okay. What symmetry does this function g of x have? So this is g of x. And if we look at it, well, you can see that if I were to spin this thing across the origin point, spin it 180 degrees, this point would go there, this point would go here, and then all these values, right, like you find this value would go over here somewhere. Actually, it would be a lot lower. This value would go down here somewhere. You know, these values would spin over this way. Everything just spins around and you get the exact same function. So this looks like it has odd symmetry. And we can prove that it has odd symmetry by taking g of negative x. That's going to be negative x to the 5th power minus 4 times negative x cubed plus negative x. Negative x to the 5th power is negative x times negative x times negative x times negative x times negative x. Pairs of x's or of negatives cancel, and we have 2 pairs. However, there's 1 remaining, so that means we're going to have negative of x to the 5th power. Just the same idea that we had for this one here. We have 3 of them, 2 pairs cancel, and we have 1 negative remaining. Same process, except now we have 2 different pairs, two distinct pairs inside this 5th power, but 1 still remains. The same thing happens for this one. It becomes negative of x cubed. And then plus the negative x is just negative x. So these 2 negatives cancel. We get negative of x to the 5th plus 4x cubed minus x. And I can take a negative outside of that. We get x to the 5th minus 4x cubed plus x. But this is the same as that. So this is negative g of x. And this is the exact proof, the exact thing that we need, that it is odd symmetry. All right, give it a try in number 1 and number 2. And then this is the kind of idea here that we're talking about in number 3, is looking at a general function analysis. You're going to kind of ask all these different questions. Do you understand how to answer each one of these things? This is a very important part of looking at functions, is seeing all these different kinds of things, being able to ask these questions. So give it a try in number 3.